Hello. Today I like to show you how to make infrasound measurements with our measurement microphones. I have here two different types. This is MP30 Ultra. So it have a frequency response from 5 Hz up to 100 kHz, which is very insensitive. And the second one, the half-inch one, it's MP30 Infra, half-inch microphone. So it is connected here to our Rugadag 4 unit. Here I have laboratory amplifier, which is connected here to this speaker. We don't see it here. But I have here a small function generator which is responsible to generate the frequency. So as first I like to show you the setup here of the DAQ system. So here in case of data acquisition, at this moment I have set up of a sampling frequency of 48 kHz. So here in this part I made before this recording here, I made a sensor calibration. So the MP30 infra microphone have a sensitivity of 45 mV per Pascal, and the MP30 Ultra have a sensitivity of 2.1 mV per Pascal. So that's so far fine. Here in this case, in order to suppress the small DC offset, I have here a high pass filter at 1 Hz second order frequency, which is now active. So means this measurement chain is now calibrated. Now I want to make kind of infrasound measurement. Here in the analysis at 48,000 Hz, so it means I have an analog bandwidth up to 20 kHz. At a FFT size, block size, so this is the number of FFT points, I have a FFT line resolution of 5.8 Hz. So now let's see what happened. I start now the measurement and just increase here the noise. So I adjusted now a frequency of 72 Hz. So we can still hear this. That's why this is standard sound, so it is not infrasound. So now we can see here something, some waveforms, because here the X scale is at 50 Hz. We don't see it now, our peak. So now I go to 40 Hz. So now we can see here. We can see here that we can see in this area our peak. It's a narrowband FFT, but this is very, it's not accurate enough. So I will stop the measurement. So if I go here to with the cursor to this point, so we can see here it is at 11 Hz, 11.7. So next point would be 17 Hz. So this is here the result of the FFT line resolution dependent on the sampling frequency. So now, if I want to make accurate infrasound measurements, it's necessary to change the sampling rate and change the number of FFT line resolutions. So means I go now here to the setup, data acquisition, and now, because I want to measure infrasound, so it's no need to sample with 48,000 Hertz. Let's say I will sample here with 250 Hertz. Okay? So 250 Hertz, apply. Now if we go here to the analysis, we can see that at 250 Hertz we have an analog bandwidth up to 100 Hertz, 104 Hertz, and now at the FFT block size of 401 FFT lines, we have a FFT line resolution of 2.4 Hertz. So this is now much better. Of course, so this is now much better. So now I will start the measurement. Now you see here the peak, where we can see here the peak. And now I reduce the frequency. So this is now 31 Hertz. So this is now 31 Hertz. So now we are at the frequency of 13 Hertz. So that means you see already, now I increase the volume. You can see now that in case of low frequency measurements, the delay and the calculation time is much longer. So for this reason, if we want to measure infrasound, we need time. So that means we need a kind of minimum time, let's say of something like minimum 2 minutes to determine the correct frequency. So for example here now in case of the FFT calculations, we can do following. We can go in the setup, in the analysis, and then we use this checkbox here for FFT line averaging or FFT averaging. So now here in the software I go to the display and change here the FFT to FFT average. So now we can still see that it's very, the delay is quite big. So in case of FFT average, if I make here this kind of noise, so then after a while, this stochastic noise phenomena will disappear slowly. So now I can reduce. For example, now it's a frequency 6 Hertz. So I restart the measurement. So here we can see now at this point, this is 6.1 Hertz. So if we want to find now infrasound source, from which direction does it come? Due to the fact that the low frequencies are relatively long waves, it is very difficult to determine from which direction the infrasound where is the source. So for this reason, for this kind of infrasound source localization, you need as first a constant signal, like here in this setup with the speaker, and then you need a long measurement time. So what you can do is following. You can, for example, if there's a, let's say, infrasound, let's say in a house, maybe generated by the heating system or some kind of pipes or air condition system. So then you may get a chance to detect it, this source. So in this case, it's necessary to be very patient and to have a long time to be able to measure this. So means, for example, I have now here the constant. You can maybe see the movement of the speaker. So it is now at 13 Hertz. We can see the movement here. And now if I don't know from where does the sound is come, from which direction. So let's say I'm now here in the area of 70 dB. So now it's about 8 dB more because the distance, I shorten the distance. So means this is the way how you can determine or how you can find the source. But you can see here in this direction. So if I put the microphone in this direction, so then the dB level is here still 70 dB. So, and this has something to do with the wave length. So for this reason, in order to detect the infrasound source, you would need 2 microphones, and then they must be separated, or the distance between these 2 microphones must be 2 meters or more. So for this reason, source localization of infrasound, it's a big challenge. And there are some kind of phenomena like the hum phenomena. So, and since the 70s, engineers try to locate this phenomena, but in practice, this is very difficult. And finally, I don't think that the real reason is recognized by the technicians. So this is now here's an example how to measure the infrasound. So that's all for today. Thank you very much and have a pleasant day.